Session we have two talks from the Bristol part of ILIKE. So first of all we have Sam Livingstone, who's one of the ILIKE postdocs, and he's going to talk about choice of kinetic energy in HMC.
Thanks. Can everyone hear me okay with this? Is that all right? Thumbs up? Yeah, good. Okay, so thanks very much for the invitation, although I'm part of the grant, so I guess that was a given. Yeah, so I want to talk about this topic, but first I want to give a brief advert. So for those of you who are still here during the third week of the programme, or if you're nearby and you want to come down for the day, on Tuesday the 18th of July, there will be a one-day workshop in this room on the following theme. Attendance is completely free, but if you're interested, come and speak to me afterwards. Okay, so this is a piece of work together with Gareth and a physicist at Bristol called Michael Faulkner. So I'm normally with Christoph. Christoph's going to talk next about some work that we've been doing together. This piece of work was with Gareth. And I want to acknowledge, of course, ILIKE and other sources of funding, and also Paul, Gabriel and Zofia, Michael Betancourt and Matteo Faciolo for useful help during the project. What am I talking about? Right, so I'm talking about Hamiltonian or hybrid Monte Carlo. So depending on whether you're from a sort of physics background or a statistics background, you'll know it under a slightly different name. And it's a technique for drawing samples from a distribution of interest which has a smooth density that I can write as proportional to the exponential of some function minus u, and u I'm going to refer to as the potential, right? So how does Hamiltonian Monte Carlo work? Well, first I introduce an auxiliary variable, p, which is typically called the momentum, and it's going to be of the same dimension as x, and sorry, this should be a p, not an x here, and I get to choose the distribution of this auxiliary variable, so I'm going to write it as having a smooth density proportional to e to the minus k, and I'm going to refer to k as the kinetic energy. So if I've now got this even dimensional system with some variables x, which I might call position, and some that I might call momentum p, I can formulate this Hamiltonian function, which is going to be the sum of u and k. So if you think about it physically, I've introduced this fictitious physical system where h describes the total amount of energy in my system. And maybe some of you have done undergrad physics or come from a physics background will know that once you have this kind of structure, this kind of Hamiltonian structure, you can define this Hamiltonian dynamics, this system of ordinary differential equations for evolving x and p such that this quantity h is conserved. Right? And in a statistical framework, why that's interesting is because I can write the joint density of x and p as the exponential of minus this Hamiltonian. So if I'm conserving h, I'm also conserving this joint distribution. So it might be a good mechanism for drawing samples from that distribution. So that's the idea. So HMC in 3 steps goes like this. You want to iterate the following. At each iteration you sample a new momentum, which is going to inject some stochasticity into your system, and then you solve Hamilton's equations, so the dynamics that are induced by this Hamiltonian for t units of time, and so this is going to propel you forward in the state space, and then you're going to get a proposal here which you're going to put within a Metropolis-Hastings algorithm. So it's a clever way of generating Metropolis-Hastings proposal. So HMC is a Metropolis-Hastings algorithm, and this is how it works. And typically, the reason for the Metropolis-Hastings is because we typically can't solve this system exactly. If we could do that, we wouldn't need Metropolis-Hastings. This would be a measure-preserving flow. But because we can't solve it exactly, we usually resort to numerical solvers, and because of that, we use this step to correct for discretization error. So just to be as concrete as possible, I've learned how to make GIFs. So this is what's going on pictorially in HMC. So what we want to do is generate a Markov chain on this kind of line, which is position space for x. So we augment the state space by introducing this momentum p, and at each step we're sort of sampling a new momentum, and that's the open circle. We pick a new momentum, and then we flow along this Hamiltonian for a certain period of time, and then we sort of project back down onto this position space, and we're building up our Markov chain here. And what you should be able to see is if you choose the sort of parameters in the algorithm well, like the time that you integrate, you're going to make quite large jumps in the state space, and this might be quite a good thing for promoting fast exploration. Okay. So that's the idea. Okay, good. Right. Okay, so what is the purpose of this talk? Well, as I said, you introduce this auxiliary variable, and we choose its distribution. And equivalently, we can talk about choosing the kinetic energy function, because that's just the negative logarithm of the density that I've chosen. So what we wanted to do was consider this kind of Hamiltonian system, and the corresponding dynamics that you'll get looks like this. So they are also influenced by the choice of kinetic energy. And we wanted to ask the question, for a given u, because u is given to you by your problem, u is the negative logarithm of the density that you're interested in sampling from, is there some sense of a good choice of k? You know? So we're going to focus on separable Hamiltonians because there are sort of well understood explicit numerical integrators for that, and that means that k does not also depend on x. So there are MCMC methods where you would make this kinetic energy position dependent. We're not going to talk about those today, although I can mention it at the end. And we want to say, you know, in some sort of broad sense, what would be a good choice, and are there bad choices? Are there things that would seem sensible to do, but actually they turns out there are undesirable consequences? And of course, all that's well and good, but we'd really like to also be able to say something practically. Can we say something to someone who wants to use HMC? Here's a few things you want to look at, and if you can understand these, then hopefully things will be okay. Okay, so well, what's done at the moment? Well, at the moment, people typically choose this form of kinetic energy, this quadratic form, which corresponds to choosing the auxiliary variable to be Gaussian. And obviously, this is a very natural choice, both just from the fact that it's the first distribution I think of, but also it has a very natural physical interpretation. If you're thinking of a true physical system on Earth, then this is the form of kinetic energy that you're going to want to use from Newtonian physics. Right? But if we're just using Hamiltonian dynamics as a mechanism for sampling from a distribution of interest, we can sort of drop the physical interpretation to some degree and just say, well, okay, what do we really need k to satisfy? And actually all you need is for it to be differentiable, symmetric about 0, and so that you can sample from it. Right. So there's quite a lot of flexibility there. And people have picked up on this in the literature, and recently a couple of alternatives have been suggested, and one of them is this relativistic family of kinetic energies, which was suggested by Liu and Peroni and co-authors. And it again has this kind of physical interpretation, but it's based on understanding the dynamics of very large bodies, right, with a very high mass. So this thing kind of looks like the Gaussian choice, so it looks like the quadratic choice of kinetic energy that you would get if you had a Gaussian momentum for small values of p, but then it kind of has slightly heavier tails, so it kind of looks more like a Laplace distribution when you get out into the tails. And then there's this other suggestion by Zhang et al. To choose this kind of family of kinetic energies which corresponds to the momentum distribution following the exponential power distribution of box and tau, or a multidimensional version of that. And they sort of suggested the fairly natural idea that, okay, well, you could pick beta to be anything you want here, so beta equals 2 will be the Gaussian choice, but actually you can vary this. And you can see that varying beta is going to allow you to vary the tails of your momentum distribution in an arbitrary fashion. And both of these pieces of work, the kind of kinetic energies were suggested, and then some numerical studies were done. And there were some scenarios where it looked like maybe this particular choice was more beneficial than the Gaussian. It was a little bit difficult to discern sort of general criteria of maybe one choice that was jumping out as optimum or something like that. So my motivation was very much more kind of bottom up, look at the algorithm from a kind of intuitive perspective and see what might be a natural choice of kinetic energy, and then kind of revisit these examples and say, okay, well, does this class have features that might benefit me in a given scenario, and similarly with this class here. And our theory is going to enable us to say something about these, and in particular also sort of what might be a good choice of beta in this example. So, okay, and just as a quick sort of link into other MCMC methods, so if you think about it, what we're really suggesting doing here is changing the kind of input noise that we inject into an MCMC algorithm. And this is a problem that's been well studied for other samplers. So if you look at the random walk metropolis and Mala, you have this kind of proposal noise that you choose, Xi, and it's kind of well known how you might want to choose this for a given problem. It's pretty well understood that if you're sampling a distribution that has kind of heavy tails, where there's kind of a large probability space that you want to explore, then you might want to choose a heavier tailed proposal noise. And the reason for that is, and the same kind of thing holds for Mala, and the reason is because in both these cases, the proposal input noise interacts linearly with some deterministic function of the current point to get what you actually get in your proposal. So if I match the tails here to the tails of my distribution, maybe I have a heavy-tailed target that I want to explore, but I'm making slightly larger moves because I've got this heavier tail proposal, and that should give me some kind of benefit. And this has been well understood, and you tend to be able to increase a polynomial rate of convergence in this setting. So the gains are modest, but they're generally worth doing. So HMC, the story is a little bit different to this. It's a little bit more complex. And the reason is because if you change the kind of input noise, the distribution of the momentum, you don't get this kind of nice linear interaction with what comes out at the end of the proposal, because you're also changing the Hamiltonian dynamics. So there's a kind of non-linear interaction between what I choose as my input noise here, and then something going on here, and what I get out in my proposal. So I might think I'm making a good choice here, but what I end up with at the end might not be such a sensible thing. So it's a little bit more subtle. Okay, the next 2 slides I am going to tell you essentially everything that we have done. So if you're struggling at this point, just listen for these 2 and then you can sort of switch off. So our intuition was to say, okay, well, can we just think about how the Hamiltonian dynamics takes the current point in my state space and transforms it into a new proposal. And if I could integrate Hamilton's equations exactly, it would look a little bit like this. Okay? Of course, we can't do that in practice. We're going to need to use some kind of integrator to do that. So if I explore the leapfrog integrator, which is what's typically used in HMC, after a single time step of the leapfrog integrator, your proposal as a function of the current point is going to look like this. And so I should just mention that some of the work we've done here is focused on the leapfrog integrator. Some bits most of it will naturally carry over with just some minor tweaks to any kind of explicit symplectic integrator that is based on the kind of Strang splitting philosophy. So there was a mention in a talk yesterday about other integrators that can be used for these kind of dynamics. Of course there are. We usually use leapfrog because it has a good balance between the kind of cost per step and the accuracy. It seems to win out in most scenarios under that kind of metric, but these results will sort of naturally carry over to a lot of other cases. So if I look at this, I've got this kind of, I'm choosing k, and then that means that this is going to change nabla k, or grad k, and so I'm going to affect my proposal in this kind of manner. And there's 2 sort of arguments inside this function. One is p, which is this is going to be the new momentum that I've sampled before I start the dynamics, so this is going to be a sample from new, and this is going to be my gradient term, which is going to depend on the current point. And I might say, well, depending on which one of these 2 terms dominates in this function, maybe I can get some understanding of how the algorithm is going to behave in different regions of the space. So if this term here, the gradient term, dominates, then I'm going to get a proposal that looks a little bit like this. And if you ignore a few constants for now, you can maybe see that there's a kind of interaction between grad k and grad u going on here. And that might be something that helps drive my dynamics and helps me understand what's going on. And similarly, if I am in a region of the state space where the gradient is very small, and actually really it's this noise that drives the dynamics, then actually my proposal is going to look a lot like a random walk metropolis, but with the noise distribution grad k of p. So I'm choosing the distribution of p, but actually the thing that feeds into the proposal is this nonlinear transformation of p. Okay, so this might be something that I really need to bear in mind as well. So based on that kind of intuition, we sort of abstracted 2 quantities that we think it would be useful to analyze. We're calling this one the composite gradient for obvious reasons. And this one we call the implicit noise because you're choosing the distribution of p, but we say you really want to understand reasonably well the distribution of grad k of p as well. Right. So that's the idea. So the main approach was this, and in summary our kind of findings are this, that if you set this composite gradient, if you try and tune k so that this thing is sort of roughly linear, especially for large values of x, then this should give you reasonable performance in practice, and I'm being very loose with the term good here, right? I'll be a little bit more precise later on with that. And this gives us some kind of interesting intuition for what sort of momentum distribution we might want to choose for a given target. So if I've got a distribution that has very light tails, lighter than a Gaussian, say, actually it's suggesting that I should choose a momentum distribution that has heavier tails than a Gaussian. So you're kind of inverting through a Gaussian to get what you might want to choose to a momentum. So it's a sort of inverse relationship compared to what we've seen for some other methods. And I'll talk about why that is a bit later on. But it turns out that there are sort of serious undesirable consequences in certain settings to choose a momentum distribution with any tails that are heavier than an exponential. So it might seem natural to say, okay, well, let's try a student's t distribution for the momentum. I've seen papers where this was tried out on one example. Actually, there can be sort of very undesirable consequences to doing that, and I'll make this bit very precise, and I'll make this bit quite precise, I think it's fair to say. Yet we've mentioned that this kind of implicit noise is also going to be important in practice. It's difficult to offer rigorous guidelines on this, but it's certainly something we should note, and I'll mention it a little bit more. I'm not going to talk during the talk about settings where grad U is approximated, either through subsampling or because it's very expensive to evaluate, but this is remarked on in the paper, and I do have a slide in the end, so if anyone's particularly interested in that, I can talk about that setting also. Okay, so I have a few bullet points here, and I'm going to attack each one of them in turn. So firstly, the composite gradient. So we have a motivating example, so I'm going to consider this family of Hamiltonians where x is just a one-dimensional parameter, so I'm introducing this one-dimensional auxiliary variable p, and I've got this kind of different tail behavior induced by alpha, so this is the exponential power family of distributions, and I want to say, okay, well, for a given alpha, is there a sort of sensible choice of beta, right? And I'll show you the proposition first, and then I'll show you some animations that kind of make sense of it. So the thing that we were looking at was the period length. So for this class of Hamiltonians, the Hamiltonian flow is periodic. So there is going to be some time at which, when you start from a certain point, the flow will come back on itself and reach that point again. Okay? And what we wanted to ask the question was, how does this period length depend on where I am in the state space? Okay? And so for this class of Hamiltonians, we found that we could relate the period length to alpha and beta, and in particular in such a way that for a prescribed choice of beta, you can sort of make it however you want. So I'll show you some pictures, some animations, and then I'll elaborate on that point. So I'm just going to do this. Good. Okay. So this is the, if I have a Gaussian target, standard Gaussian target, and I choose a Gaussian momentum distribution, and this is a well-known phenomenon, that this period length, the time it takes to come back on yourself, is independent of the current point, right? So the flow speeds up in exactly the right degree to which you have to travel further as you go further out, so that you get this really nice trade-off, and wherever you are in the state space, it's going to take you exactly the same time to come back where you are. And we'd argue that this is a very desirable property. The reason is because if you've sort of chosen a good integration time for your algorithm based on one region of the space, it should also be a pretty good integration time in a different region of the space. And another thing that's known about this is it's in some sense the fastest you can make your Hamiltonian flow go, so that it's still able to numerically simulate it well with a very simple explicit integrator like Leapfrog. Okay? So if I just show you what happens. So in this example, here now we have a slightly heavier tail distribution we're trying to sample from. Okay? And if I choose the Gaussian momentum distribution, what you should be able to see is it takes this amount of time then to go around one period, but it takes a little bit longer as I go further out into the state space. So this flow will be robust to numerically simulate, but it might not be as fast as I'd want it to be. Okay? And so this is not so bad. What's a little bit more dangerous is this scenario. So here I have a very light tail distribution that I'm interested in sampling from, and if I choose the Gaussian momentum, well, what you can see is actually the period length decreases as I make x bigger. So the flow gets very, very fast out in the tails. So the amount of time it takes to do one circle here I can go around over 3 times in this setting. And this is quite bad because this is the setting where numerical integrators are going to become unstable for large values of x. So if I think intuitively about using a kind of explicit integrator where I'm assuming that the gradient is constant over some small step size, then if I've got this gradient that's changing wildly, then, and assuming it's going to be constant over any fixed step size, is at some point going to give me some problems. So our result says that actually, if you've got a given alpha, so in that last example alpha was 4, the period length is a function of E, which is the value of the Hamiltonian at that point, the current energy, to the power of eta, where eta is this expression in terms of alpha and beta. So in particular, if I choose beta to be 1 plus 1 over alpha minus 1, actually I get eta equals 0, and I get this phenomenon that happens with the Gaussian. For any value of alpha bigger than 1, I'll get the same effect that the period length becomes independent of the current point. So if I choose beta equals 1 and beta equals 2 and alpha equals 2, which is the Gaussian case, then this is going to, the numerator is going to cancel this with 0, but I can do this more generally. So if I just revisit that last example, and now I choose a slightly heavier tailed momentum, in particular e to the minus x to the 1 plus 1 over 3, then I recover this period length being independent of the current point. You see now all of the different flows take exactly the same amount of time to get back to the current point. So this is just intuition based on a simple class of potentials, but this is a kind of, I think it's quite informative for understanding why we are recommending this composite gradient to be linear, because this is what happens if you choose beta to be 1 plus 1 over alpha minus 1. And so, like as we're saying, intuitively it's giving you the kind of fastest Hamiltonian flow that you can numerically simulate easily, okay, with current algorithms that are used in HMC, with current integrators. Okay, so I'm going to make these ideas a little bit more precise and a little bit more general, and I just want to define a couple of notions before I do that. So I'm going to call a distribution heavy-tailed if it's heavier-tailed than an exponential. And I'm going to call it light-tailed if it's lighter than an exponential. So this is the kind of cutoff that I'm considering. And if it's lighter-tailed than an exponential, then that means that this grad u is going to grow with x. And if it's heavier-tailed, then it's going to shrink and become negligibly small. So it's known that HMC, with the standard choice of a Gaussian momentum corresponding to a quadratic kinetic energy, it's known to struggle in terms of it won't produce a geometrically converging Markov chain, a fast converging chain. In these two settings, one is when pi has heavy tails, okay? And 2 is when this gradient of u grows faster than linearly. Right? And the first of these is because the Hamiltonian flow is too slow. It doesn't matter how well you're numerically approximating it, the flow itself is too slow, the dynamics aren't giving you fast sampling. And the second, the dynamics itself are really, really fast, but they're too fast to be simulated efficiently with Leapfrog. So we have the following extension of that result. So it turns out in the first case, when pi is heavy-tailed, there is no choice of kinetic energy which is independent of x, which will give you a geometrically converging chain. And for that reason, we're focusing more on this scenario where you've got a sort of light-tailed distribution. And we have the following natural generalization which says that it's really when this composite gradient grows faster than linearly that you're going to run into these numerical problems. Okay? So, and this is a natural generalization because when k is just a quadratic function, then grad kp is p. Right? So in that case, I can just hide this bit because it's just the identity map, and I recover the original theorem that it's the gradient that I should look at. So it's kind of alluding to saying that, look, in general, it's this composite gradient that you want to look at. Okay, so I have the following extra proposition. I don't want to talk too much about it. I'll just say that we derive this intuition based on looking at a single leapfrog step. But HMC is advantageous principally because you can take lots of leapfrog steps. You can integrate for a long time while still preserving the energy reasonably well. So you might ask the question, well, this intuition we derive from one leapfrog step, is that still going to hold over multiple leapfrog steps? And this proposition is just arguing that yes, it will, in the sense that your sort of proposals won't blow up if you choose your potential and if you choose your kinetic energy given your potential in a way that this composite gradient is at most linear in growth. And that's kind of contrasted with the Gaussian choice, where if you've got a quite light-tailed here, you will get these proposals that blow up. And this is well known in the Gaussian case. Okay, so that's the first bullet point where I wanted to convince you that this composite gradient being roughly linear might be a good idea. Now I'm going to turn to the idea that some choices of kinetic energy, principally those that will induce a heavy-tailed momentum distribution, might not be a good idea. Okay? So we make this quite precise. So first I want to show you another animation, the final one. So this one I am choosing a Gaussian distribution that I want to sample from, but I've chosen a Cauchy momentum distribution, so something heavy-tailed. And the following happens, right? So in the center of the space, I'm still doing okay. I'm still sort of going around in reasonable amount of time, but as I go out into the tails of my state space, actually the flow gets so busy trying to travel this level set in the momentum direction that actually you hardly move in the x direction. So you get these moves that don't really cover any distance in my space. And we make this precise with the following argument. We define this idea called the negligible moves property, and I'm sure similar ideas exist in the Markov chain literature already. We say that for any choice of delta, there is a kind of region in my state space, x, such that if I am currently at the point x, the probability that my next point will be in some ball of radius delta will be arbitrarily high, right? And this is for any delta, so I can make delta really, really small. And so you can see that it's really saying this is a property that will mean my Markov chain doesn't move very fast, right? It doesn't move very far. And intuitively you think, well, this doesn't seem like a very desirable property for a Markov chain to have, and we would agree with that. And the proposition we have is, well, if pi is light-tailed and the distribution for the momentum is heavy-tailed, then a Markov chain produced by HMC will possess this negligible moves property. So there are certain regions of the state space where the sampler is going to move very slow. So I said this might not be a very good thing to happen. The natural question is, will it preclude geometric convergence? Will it stop the kind of desirable properties that I want of my Markov chain? And the answer is actually no, it won't necessarily. And the intuition for that is that I might have these moves that only move an arbitrarily small distance, but that distance will be kind of deterministically in the right direction, right? So it might be that they're very slow, but they're definitely going to the region of the state space that I'm interested in. So here's a very simple example where this is going to be the case, where I just take a Markov chain by perturbing the current point by -1 and adding some noise, and it's known, this is a sort of standard thing that people look at in the Mine and Tweedy style literature, and it's known that this thing is geometrically ergodic, and if you just transform it by taking logarithms of all the points, then you're still going to get a geometrically ergodic chain, but it will have this property. So there's a simple counter example, right, to say that you can still recover geometric ergodicity. So what's going on here? I told you this thing, I told you it was bad, and then I'm telling you maybe it's not so bad. Well, it kind of still is not great, and the reason is that when you've got a geometric ergodicity bound, you have a kind of rate function which depends on the number of iterations. You also have this Lyapunov function which depends on the kind of current point. And if you have this negligible moves property, then any of these Lyapunov functions have to sort of grow faster, strictly faster than exponentially in x. So what it tells you is you can still have a geometrically converging chain, but the penalty for starting in an undesirable region of the state space can be very severe. Okay? So that's the kind of intuition we've had here. Okay, that's the second bullet point, right? So I'm on to the last one, which is this implicit noise, and I said we don't really have any concrete theory because it's going to depend on what examples you're considering, but I just thought it was useful to give some examples of where you might choose what seems like a sensible distribution for your momentum, but the resulting transformation grad k of p might not look so desirable. So our intuition is, well, you probably want to choose this guy in a way that would mean that its distribution is something you might naturally choose in a random walk metropolis, right? Something that looks maybe Gaussian, maybe close to Gaussian. But if you choose a Laplace distribution for your momentum, for exactly this thing is going to look it's either going to be -1 or 1, each with probability half. So you're going to get these moves that move according to very discrete jumps, right? So if you have a distribution where the value of the potential changes quite rapidly, this kind of discrete jump, you might miss miss this kind of point in the middle, and it might be a very undesirable thing to happen. We do have an example, which I might get onto, showing this kind of behavior. And particularly in this kind of exponential power family that I showed at the start, if you choose this beta to be kind of close to 1, so for example 4/3 here, you're going to get this kind of bimodal behavior where the moves concentrate around -1 and 1, so you're going to get this blocky type of proposals. Sometimes this might be okay, but as I said, there are going to be examples where this might not be the thing you want to do. So in the absence of further information, we kind of recommend doing something that does look a little bit more like a Gaussian in the center of the space, so when p is small. As I said, we don't have any strong theory for that, it just seems like a sensible thing to do. Okay, so general guidelines, and there is a kind of thing that we're calling a robustness efficiency trade-off in the paper. So as I said, I think we want to choose this composite gradient to be roughly linear, especially for large values of x, and this is going to give us a good balance between the speed of the flow and the ability to efficiently numerically simulate it with a simple method. Statistically, you can think of this as forcing your chain to kind of be autoregressive in the tails. And the intuition for this composite gradient is the more sort of sublinear in x you make it grow, the slower you make it grow, the slower the flow, but also the more robust you can be when you simulate it numerically. So you could probably get away with a larger step size. It will still give you a kind of reasonable behaving algorithm. So the extreme case of that is if you have something with Laplacian tails, and then for large values of x you're going to get a composite gradient that's just the sine of the gradient of u. So it doesn't matter how fast this thing blows up now, I'm always going to have it stabilized, and this is always just going to be 1 or -1. So always going to get this unit speed flow. So this would be a very safe choice. And intuitively it does seem sensible to look at this implicit noise, and in the absence of further information, making it look close to Gaussian wouldn't seem like a bad idea. Okay, so lots of intuition. Here's a couple of cases where it might be how you might choose this kinetic energy in practice. I don't think it's too difficult to do. We've got a couple of instances here, and then I'll just give you 1 or 2 examples depending on time to finish off. So the first one is, okay, if I'm just sampling from a multivariate Gaussian distribution with a covariance matrix of sigma. So I get the following gradient of u. And it turns out that our theory would imply that actually we want to choose the momentum distribution to also be a Gaussian, but with the mass matrix to be the inverse of sigma. Right. Now those of you that use HMC and have used it in practice will know that this is the guidelines that we already intuitively have by relating a single step of the leapfrog integrator to Langevin diffusions. Right. So we intuitively actually already have this idea that if I've got a proposal that is maybe slightly lighter in scale than the Gaussian, the standard Gaussian, I want to choose a momentum distribution that is slightly heavier in scale to kind of balance these things out, and that's going to give me the sort of sampling that I want. And really all we're saying is that you can extend this kind of intuition to the shape of the distribution. If I have a distribution I'm sampling that is lighter tailed than a Gaussian in shape, I might want to choose something that's slightly heavier tailed, right, to balance that out. So it is, in some sense, it's a natural extension of this idea. So if I look at it now for another example, so this double well potential, which is something that's considered a lot in statistical physics. So you've got a kind of a probability density which has 2 modes and that decays very sharply in the tail. So it's very light-tailed and it's got a bit of multimodality in there too. And you can see this gradient, you've got a x to the 3 term here, which is going to cause you problems in some settings if you just use the Gaussian choice of momentum. But this would motivate a choice of kinetic energy which has a gradient of p to the 3rd. And you can see it quite intuitively, because if you just wrap a parentheses around all this and put a 3rd at the top, well, you're going to make that cubic term now linear in x, right? So this isn't something that's going to give you sort of composite gradient equaling x all the time, but you can see that I'm slowing down the kind of problematic term in the sense that I'm going to get a more stable sampler as a result. So that's a kind of pretty intuitive way that I can go about choosing this. And obviously there are lots of other choices I could make which would give you the same kind of behavior. So whenever you can write down this gradient of u, I think you can sort of engineer kind of kinetic energy in the way that you might want. Okay, so I mentioned a couple of choices earlier on. Yep. The relativistic choice and the exponential power choice. And the relativistic choice, we can now retrospectively analyze these, and the kind of relativistic choice, I said it behaves like a Gaussian in the center of the space. So in terms of this implicit noise, it's doing something quite desirable. It's giving me things that look like Gaussians. And then it has heavier tails, like an exponential distribution, which will correspond to this setting here, where my composite gradient looks like this in the tails. So it's very robust. It's got the right sort of implicit noise, but you might be able to go a little bit faster, right, if you tune this thing a little bit more carefully. The exponential power choice, we had this beta, which will allow us to completely control the tails. So this is giving us the right ability to tune this composite gradient, but as we saw some examples in the center of the space, this implicit noise can be a little bit undesirable. It can give you this kind of bimodal behavior, which might not be what you want, depending on your application. So an obvious thing to do would be to try and combine the two in some way, and that's sort of what we've suggested here. So you can see that this choice here, if P is smaller than this tuning parameter gamma, then I'm going to get Gaussian-like behavior for my kinetic energy. So, but when P is much larger, then I have these tails which are controllable through beta. So the implicit noise is close to Gaussian, but I also have power over this composite gradient. And just look at a couple of examples to finish. So we've tried this out. The first one we wanted to look at was a quantile regression. So this is a pinball loss function. It's actually a smoothed version of the pinball loss function, which Matteo, Faciolo and Simon would have developed, so that we can safely differentiate it. And we're outside of the framework of full Bayesian inference here, because this is a loss function, so we're relying on Chris Holmes and others' general Bayesian updating formation. And the reason we chose this example is because this loss function is linear in beta, right? So I've got a prior here, and I can choose Q to be bigger than 1, and then this term is going to be the dominant one, right? So I can safely sort of tune my kinetic energy in the way that I want. So we did two experiments, one with Q equal to 2, so Gaussian priors, and one with Q equal to 1.5, which would correspond to one case of the bridge estimator. Okay? And in each case, we just sort of took the sampler out to quite a far away point in the tails and saw how it behaved, how long it took to get into the center of the space. And the results were like this. So this black dotted line is the Gaussian choice of momentum distribution, and in the case where we had Gaussian priors here, then this would tell us that this is the optimal choice, and indeed it is the one that converges the fastest. This solid grey line is the Laplacian choice, and you can see it has this quite sort of stable unit speed flow. And this one here, the dotted grey line, is a student's T distribution with 4 degrees of freedom, and what you can see here is the negligible moves property in action, right? Because for the first few thousand iterations, the sampler hardly really moves. Okay, so this is a manifestation of that property that I showed you earlier. So when we change Q and make it slightly so that the distribution for beta is slightly heavier tailed, we now have this extra line here, which is solid black, which is actually e to the minus x to the power of 3, absolute value of x to the power of 3. So it's a lighter tailed distribution than the Gaussian. So this would produce an unstable algorithm here, which is known to not converge geometrically. But here now it is numerically stable, and it converges faster than the Gaussian. This is kind of matching our theory, although obviously it's quite a simple example that I really just wanted to show this property with. A second example we've got is a 1,000-dimensional parameter space, which is the Ginzburg-Landau model from statistical physics. So what you've got here is a kind of a double well type potential. You've got a quartic term here and a quadratic term here, and you've got this term in the middle here, which induces correlation between neighbouring sites in a lattice. Okay, so each individual site has this kind of multimodal, very light-tailed behaviour, and you can control the degree of correlation. Okay? And so we did two experiments here. One, we sort of started the sampler at a very favourable region of the state space, and we had a look at the kind of effective sample sizes. And the second example, we started it from a kind of random start between -5 and 5, and we just wanted to see whether the sampler was pretty robust to different starting points. And we got the following example. So the mean effective sample size for the mean at equilibrium. So we got the best choice here was with the Gaussian. So what we found with this system is, even though it's known that the Gaussian momentum won't produce a geometrically ergodic chain, so you may not trust these values, in practice for this system we didn't observe any kind of divergences on the timescales of the simulation. So that is going to be the case sometimes, and sometimes you're going to see a lot of divergences. So if we started it here, it performed okay, and it mixed the fastest because it is giving you a fast flow. This kind of choice that we advised was second. The relativistic was slightly slower because it's quite sort of stable. And the exponential power choice, even with the sort of guideline, was a lot worse. And the reason for that is because of this bimodal implicit noise that it induced, we had to choose a very, very small step size because this is a case where the potential grows very fast in a very short period. So we were finding that we had to choose the step size to be very small to promote stable behavior. So it's demonstrating that the implicit noise is something you want to tune. The second example, where we just randomly started all the points between -5 and 5, and we saw how long it take for them all to be between 2 and 2, then it has slightly different sort of results. This time the Gaussian got stuck every time, right? It's known that it's unstable here, so it didn't manage to get to the center of the space. And the other three were all stable, and the kind of the best one was the one that we chose here. So these two should have the same kind of behavior, but because I had to choose a smaller step size in the latter case, that's why it was a bit slower. Yeah. Okay, so I think I'll finish there. So thanks very much for listening, and here are some relevant references.
Any questions, Hassan?
Yeah. So what is the most important for you? Is the speed or the robustness?
Well, I think both are important. It's going to depend on the specifics of your example, but if the convergence time is not too bad, then probably robustness is a really good idea. If you're in one of these situations where your algorithm might take days, then any gains in speed are probably worth tuning a little bit. So the faster you make it, the more careful you have to be with tuning the algorithm. So it's just if these gains in speed are worth the extra time in tuning, is what you really want to consider.
So could you fix the speed of rotation by tuning epsilon in details according to the magnitude of the gradients?
Yeah, you could. Yeah, so a position-specific step size would be another option. So there are sort of methods that there is a paper on that. It sort of corresponds to the same kind of idea as the Riemannian manifold idea, where you're actually choosing a position-specific function of momentum distribution. So it's depending on x. So you have to again choose a slightly different integrator, and it might end up being implicit. So, but yeah, that's another way around this.
Any further questions? No, great. Well, let's thank Sam again.